My name is Max, and I'm head of security engineering at Zoom. I'm here to talk to you today about how we built in end-to-end encryption to Zoom's meeting product. In May 2020, we published a white paper on GitHub that describes our phased approach for introducing end-to-end encryption and identity into Zoom's meetings. We got a lot of great feedback on that paper from the community, so thank you very much for that. A few months later, we had a prototype. And this is a picture of the first ever end-to-end encrypted Zoom meeting, which I was lucky enough to be a part of. In October 2020, we released to the world the first version of the Zoom client that had end-to-end encryption, which is available to both paid and free users alike. So we recommend you try it out today. Today, I want to talk to you about what it took to get there. So the first thing I wanted to talk a little bit about is what's the landscape out there for video conferencing security? What are other people doing in the field? I also want to mention briefly what encryption looked like at Zoom before end-to-end, how we overcame challenges to offer end-to-end, and what features we intend to offer in the future. So what's out there? The most basic setup for video conferencing is as follows. Alice and Bob connect to a server via something like a TLS protected connection, and they're going to exchange video conferencing data, whether audio, visual, screen share, through some common server. And this could be a cloud-hosted server in a lot of cases. And so I say Alice and Bob are using TLS here because it affords them a lot of protections. It protects them against their ISPs or their local coffee shop from intervening on their connections. And so obviously they're getting a lot of protection. And the server in this scenario gets to see the plain text of the conversation. And this is quite useful if you consider someone like Carol coming into the conversation on a phone on a bad connection. So imagine Carol has a 3G phone and she can't handle the full throughput of the conversation. Well, the server can downsample video and audio for her so she can get a good experience, while Alice and Bob both get to enjoy full resolution. So this is the way a lot of video conferencing software works today. What are the issues? Well, the problem here is that the server has access to the plain text. And let's think a little bit about what can go wrong with point-to-point encryption. The problem with this approach is that all the bad guy really needs to do is get access to the server and just listen. They don't need to inject any new traffic. They don't need to perform any interesting social engineering. All they have to do is copy the data that's flowing through the server. And this is very hard to detect. If an attacker is good at this, they shouldn't leave much of a trace. And when you think about who might actually want to do this, there's a large list of people who could do it. The first group that comes to mind is if this is some sort of commercial product, employees who work at the video conferencing company might be able to interpose on meetings. And you can think about disgruntled or compromised employees. There might be a lot to gain. A bad actor who has access to the cloud infrastructure that's underlying this server might also get access to the meeting. And so if you think about it, that a lot of providers these days don't actually rack their own physical software, obviously that introduces a new risk. There's a whole other party of people who can get access to the infrastructure. And finally, an attacker who gains access past the perimeter of this infrastructure might also get access to the meeting. If you think about the way a lot of servers are set up, it's usually there's a secure perimeter, but once you're inside of it, you can do a lot of damage. And the same goes for, obviously, video conferencing, that any attacker who gained access to the video conferencing server can exfiltrate the meeting data. Now, I would make an obvious point here that meetings can be extremely valuable targets. And especially in the age of COVID, when a lot of things have gone virtual, some very high value meetings are happening virtually. And you can think about board meetings of Fortune 500 companies or meetings of government regulators. And these are very valuable targets, and the rewards, financial rewards for exfiltrating meeting data might be quite large. A lot of times people come up with another solution to the problems I just mentioned in the previous slide, which is what I would call an on-prem solution. So imagine a bank who wants to do video conferencing, but maybe they didn't want to be subjected to the cloud risk that I showed in the previous slide. Well, what if the video conferencing provider shipped them some sort of software that they can run on-prem, and then they can run their meetings that way? Well, here's my list of risks that I showed previously, and they're almost all also risks for an on-prem solution. The one I would say is like there's no longer risk of cloud infrastructure being compromised, but attacks of an on-prem video server, I mean, they could be just as hard to detect. And there's still bad employees who are at play. And it's not just, in this case, it's not the employees of the video conferencing provider, it could be the employees of the bank who are the ones who might exfiltrate the data, especially if of executives. They might be incentivized to do that. Again, the on-prem solution would have a perimeter to protect, and the value of the target is not going to be decreased as a result of running a server on-prem. The one thing I will say is this on-prem solution introduces a new risk here is that the software itself can now become a backdoor onto the prem. And so because video conferencing requires publicly visible ports, these ports might be the way that the bad guy gets in. So there are risks involved with an on-prem solution as well. So this is the context in which we decided to introduce end-to-end encryption into the Zoom product. And we think end-to-end solves a lot of the risks that we saw in the previous slides about having some sort of centralized server that's seeing the plain text of a meeting. Now, before I get into end-to-end encryption at Zoom, I wanted to describe a little bit about how encryption at Zoom worked before we got here. And the one thing I will say at this point is that if there are any questions throughout the presentation, please enter them as we go, because I'll be taking questions and hopefully answering them as I do the presentation. So in enhanced encryption, which is what encryption was called at Zoom before end-to-end, the process is as follows. Alice, Bob, and Carol connect through some sort of cloud-hosted meeting server. And in order to protect their data, as we saw in the first point-to-point encryption examples, the server is going to cook up some 32-byte random meeting key that is then going to be used to symmetrically encrypt meeting streams that are sent between the participants. And it's going to use some sort of standard encryption algorithm like AES-GCM. Now, the server knows the meeting key that's being used to encrypt, and it typically doesn't use it, but it does in a very important case. And that is, let's say Alice, Bob, and Carol want to invite their fourth friend, Doug Cullen, who's on an old-fashioned PSTN phone. Now, the Zoom server, because it knows this meeting key, has the credentials with which to patch in this old-fashioned phone call, and therefore it can send decrypted data to the phone and get data from the phone and encrypt it and inject it into the meeting with Alice, Bob, and Carol. So we will make the point that for a non-end-to-end encrypted meeting, there's still an advantage of the server seeing the plain text, and that is to do something like patch in a PSTN phone, or maybe to do a cloud recording. So here's how end-to-end encryption works. And we're going to describe it in a pretty simplified way, but that gets the general point across. So the key idea here is that the server never gets to see this meeting key. Rather, that the participants, in this case, Alice, is going to be the one to generate the meeting key, and she's going to use public key cryptography to distribute it to the other participants of the meeting. And as we said before, there will not be the possibility of a phone dial-in because the server is not able to bridge the connection. So here's the protocol for what might happen when a meeting gets bootstrapped. So call Alice the leader, and she's the one who generates this meeting key. Now, Alice, Bob, and Carol all have identity signing keys that are associated with their devices. So the device keeps the secret key of this signing key in its storage, and that key never leaves the device. The public side of this key is sent to the server, which in turn will broadcast it to the other participants. Next, Alice, Bob, and Carol will generate Diffie-Hellman ephemeral keys just for the purposes of this meeting. So each of them will generate a secret key which doesn't leave the device and a public key which does. Now, what they're going to do is sign that public key with their long-term identity and send that signed public key up to the server, which in turn is going to broadcast it back out to the other participants. Now Alice is ready to do a key exchange. So she's going to perform a Diffie-Hellman key exchange, one with Bob and one with Carol, which is then going to give her a shared secret with Bob and Carol respectively. She's then going to use that shared secret to send the meeting key over to Bob and Carol so that now Bob and Carol get the meeting key, but the server never gets to see it. And as before, that meeting key is going to be what's used to encrypt audiovisual data as it flows through the server. Now, when Carol leaves, the key ought to be rotated. So Alice performs the whole operation again. She makes a totally new meeting key that was not related to the prior one. And then she uses the same Diffie-Hellman key exchange to send an encrypted copy of that meeting key to Bob. This provides the property that even if Alice were to get the ciphertext of the meeting after she left, she wouldn't be able to decrypt it because it'll be decrypted with a new key, MK sub 2, that she didn't have access to. There are a lot of important ways that the end-to-end encryption design that we have in Zoom works its way out into the user interface. And this is one of the better examples of it. So the way it currently works, that at least every 10 seconds, the leader, in this case, Alice, sends a heartbeat message to the other users in the meeting, Bob and Carol. And this includes some important information. First, the current key generation. So are you on MK1 or MK2? And also a list of meeting participants who know the key. And so this way, Alice can look at her user interface and know exactly who's gotten keyed into the meeting. Moreover, the other people in this meeting can also see the same view. And so if Alice was in the meeting expecting only Bob and Charlie, and she sees Doug in the meeting, she knows that there's a problem. And there's no way for the server to inject a Doug without it being reflected in the user interface. Now, the reason we send this every 10 seconds is that we say a malicious server might withhold these updates to potentially hide the fact that a new member has entered into the meeting. Well, in that case, the client will disconnect if it misses enough of these heartbeats. We'll make the point that at this phase of our design, these display names are arbitrary, meaning people in the meeting get to type the names themselves into their Zoom clients. There's obviously social pressure to do something reasonable here, but in the future, we hope to really make some good improvements upon this by providing stronger notions of identity. As with a lot of other end-to-end encrypted products, there is a risk of a meddler in the middle, or what used to be known as a man-in-the-middle attack in this configuration. And it's the basic man in the middle that you've read about for years. It's that Alice and Bob think they're connecting to each other, but rather there's a malicious Eve in the middle who's doing some fancy footwork with regards to swapping out their public keys and injecting her public key. And you want them in a scenario where everyone's connected to Eve and they don't know it. Now Eve gets to decrypt the whole contents of the meeting. So in Zoom phase 1 end-to-end encryption, we provide a countermeasure in the form of a meeting leader security code. And so what Alice ought to do is she should click a button on her user interface that exposes a code as you see here on the slide. She should then go and read that code out to everyone else in the meeting, who should check that their clients show the same code. And if that's the case, they know they're not being meddler in the middle. Now, as you can imagine, this is not the cleanest user interface, but it's the simplest way to provide meddler in the middle protection into the framework that we've established. There's another point here too, which is that if Alice drops out of the meeting and maybe Bob now becomes the new host, the UI has to reflect that fact. And it ought to say that a new meeting code exchange should happen. And this is something you would see in Zoom's client today. And as I said, we're not fully satisfied with this UX. We worry that a lot of our users might skip this step, in which case there's no way for them to be guaranteed that there isn't a meddler in the middle. Another thing we can do to prevent this type of attack is this nice feature called lock the meeting. Once Alice has let her other participants into the meeting, in this case, Bob and Carol, she could push a button that says lock the meeting. This prevents her client from letting anyone else into the meeting that she doesn't want there. And if you combine this feature with the previous feature, the meeting security codes, you have a pretty good guarantee that if you do the meeting code exchange once, you never have to bother with it again for the purposes of this meeting. So that was a brief description of end-to-end encryption phase 1, and I laid out a case that there's a little bit more work to be done here. And this is coming in phases 2 and beyond. And we're going to go through what that looks like right now. And the bread and butter of phase 2 and beyond is a notion of better identity. And there are two things that we'd like to say here. The first thing that comes to mind is that Alice, if she's talking a lot to Bob and Charlie or Bob and Carol, can she bookkeep some state so that she doesn't always need to do the same meeting leader security code exchange that we saw previously? And the answer is yes, she could do something that's called TOFU, or trust on first use, which means that when she first meets Bob and Carol, it could be something where she has to do an exchange, but every subsequent meeting after that, she should be able to leverage the fact that she previously authenticated them. And what she really needs to do is write down their public keys so that when she sees those public keys again, she doesn't have to expose a warning that this is a new person. And the other part of the identity that we hope to provide is that that we're thinking hard about how to move trust in what your identity means away from Zoom, the service provider, to other third parties that our users are trusting already. And we think the best candidate for this is what's called an identity provider, or an IDP. And these IDPs are what our customers are currently using today to manage SSOs, or single sign-ons. And so our thinking here is that our customers are already trusting these services to authenticate their users and also to maintain a notion of a roster for their company. Can we leverage this fact to expose that identity into meetings? So let's go over the TOFU portion first, and then we'll hit the third-party IDP design a little bit later. So here's a basic screenshot of what it might look like to do a TOFU style security upgrade. So imagine this is a four-way meeting, and let's say for now I'm the person Alex. Alex might be talking to Carol all the time, in which case his client, can reflect the fact that this is Alice, that this is Carol who Alex talks to all the time. But if Bob and Alice show up for the first time, or maybe Alice shows up on a new device, Alex can be in a position where his client can alert him to that fact. And this is going a long way towards reusing the security code exchange, so you really only need to do it once or a handful of times. Now, a problem comes up right away, though. And you could imagine if the most simple implementation of remembering people's public keys is just writing down other people's long-term device signing keys that we saw in the key exchange. Well, look at the case of where Alice and Bob have 3 devices each. So when Alice and Bob first communicate, they'll get a warning, but they'll also get a warning whenever they communicate on a new pair of devices. And so there are 9 total pairings, which means 9 possible warnings for Alice and Bob if each of them have 3 devices. And you can imagine they will get so used to seeing these warnings, they'll just start to ignore them, and they'll have warning fatigue, and in which case the warning doesn't do much of anything. And moreover, this problem doesn't go away. It continues whenever either one of them adds a new device. When Bob, in this case, adds a 4th device, there need to be 3 new warnings. So can we do better? And the answer is yes. In our proposal, we have a notion for how Alice and Bob can get away with just 1 warning when they talk to each other for the first time on any of their devices. And really what this looks like is both Alice and Bob should have a notion of a personal device cloud. They should have a handful of devices, any one of which is authorized to speak on their behalf. But as long as any one of those devices in the cloud speaks to any of the other devices in Bob's cloud, then that's the only warning you need. That's the TOFU warning that has to be presented to the user, and the rest can be handled automatically without warnings. Moreover, if Bob adds a 4th device, there should be no additional warnings as long as that device has been authorized by Bob. So this would be a big improvement. How do we build it? Well, let's start building up a notion of identity for Alice. The first thing we want to do is commit her to something like a long-term identity that she's going to expose to other users. So maybe there will be a display name, like a human readable name, and maybe an email address in case there's any ambiguity in her human readable name, and also a set of devices that constitute her identity. So in this case, Alice has 3 devices, 3 public keys. Each of those devices has a secret key, a corresponding secret key to that public key that never leaves the device. And a typical flow for Alice might be that she first signs up with a laptop, later adds a phone. But when she adds a phone, it has to be approved by one of her previous devices. So in this case, her laptop. And then later she might add a tablet. And as long as that's approved by one of her previous devices, be it her laptop or her phone, that device now becomes part of her identity. So let's drill down a little bit on what this approval process actually looks like. There are 2 things that happens when an old device approves a new one. The first is that the old one delegates signing authority over to the new one via signature. And this means the old client used to be able to sign on behalf of Alice. It's going to sign a statement saying the new device is able to sign on behalf of Alice too. But But there's a second thing that happens here that's totally independent, and that is the old one might have some private keys used for encryption and secrets that it can gossip over to the new device. And so this way, the old device and the new device can share secrets through the server in such a way where the server can't see them. This is going to be important later in the talk. And it's a very powerful mechanism that unlocks a whole bunch of new features. One last thing we want to describe here is that when Alice revokes a device, she should sign a statement to that effect. And so in this slide, Alice threw away her phone or she left in a taxi cab. She should sign a statement with one of her other devices saying to no longer trust that device. So now we can improve upon the contact sync UI that I showed you earlier. So if you recall before, we had a pop-up that said Alice is on a new device. In this case, we don't see that. So everyone else remembered the fact that spoke to Alice on her old devices, and when Alice delegates to the new device, they're happy with that and they don't need to show a warning. Now, of course, when Bob shows up for the first time, you do need to show that warning. So we've gotten rid of one of the two warnings. Now, if you consider the fact that Alice is going to be speaking to a lot of different people across a lot of different devices, there's a notion that she needs to sync this record of who she's spoken to through the server so that her other devices can see it. And we thought pretty hard about how Alice would want to do this. The naive way would just be to write in plain text, signed statements from Alice on the form, like I just spoke to Alex on my phone, or I just spoke to Alex, on his phone, or Alex on his desktop, and then sync that across her devices. But we were quite worried about accumulating all of that valuable data on the server. And if it were ever exfiltrated, it would be extremely damaging to a lot of people. So instead, what we're building is that Alice is syncing an encrypted copy of this contact history so that even in the worst case scenario, if this data is exfiltrated, the attacker can't see who Alice has spoken to. Now, you might be saying, well, the server knows anyway who's spoken to who. It probably has logs as to who joined which meetings. That might be the case, but those logs will be thrown away all the time. And these contact histories might go back a long distance to prevent Alice from having to re-authenticate other people in her contact book. So there's a real advantage to encrypting these records as they're synced through the server. So that's the UX we're trying to build up to. Well, what's the mechanism? And here we're introducing an idea in our paper called signature chains. And so, as I said before, Alice has a series of devices that she's introducing and approving and potentially revoking. And each of these operations should be serialized in such a way where replaying them in a different order isn't possible. So what that means is that Alice makes a first device, in this case her phone, on link number 1. In link number 2, she might provision a second computer, which in this case is a laptop. Now that might also be self-signed, but she's also signing the fact that this is link number 2, and she signs a hash over the previous link, which is link number 1, saying that this can later only be played in one order. Now she'll go back to her phone and approve her laptop, and that's another signed statement. And finally, she might revoke her phone later with a laptop, and that's a fourth signed statement. And so the advantage of a signature chain is that Alice performs these signatures in such a way so that they can only be replayed in one possible order, and that a malicious server can't reorder them in a way to get the wrong answer. So that's the first building block, but there are a lot of attacks that are still possible if you're considering a malicious server here. And the first the most obvious one is that the server might withhold the end of these chains. So the server might have shown Alice the extent of her 4 links in her chain, but then when Bob goes to ask what's Alice's identity, he would need to play back this chain. But let's say the server withheld the fact that Alice revoked her device. This might be a very valuable attack if potentially the server wants to show Bob that revoked device, so it can withhold the end of the chain. Another attack is that the server might try to fork Alice. So it might show Alice might be asking for her own identity on a new device, and she might get a shortened version of that identity chain, one that potentially leaves off the last link. Now, when Alice goes and adds a new signature to it, she'll fork the chain and potentially remove that revocation. So this is a way in which the server can play a game on Alice so that Alice herself signs a truncated or forked version of her signature chain. And finally, the server can do something pretty fancy here and just wholesale substitute what Alice wrote with an evil attacker. So, Alice might ask the server what's my signature chain, and she might get the right answer. But when Bob goes to ask the same thing, he might get a totally different chain that has nothing to do with what Alice signed. We can call this a substitution attack. And so in all of these cases, we are building up a mechanism to avoid this whole class of attacks. And the solution, which you could read more about in the paper, is called a transparency tree. So the idea here is to store all identities in an authenticated structure, similar to what you might see in the Keybase product, the Connix paper, Key Transparency, or Seamless. And the idea here is that this data structure is append-only, privacy-preserving, and auditable. And it's working towards building this guarantee that all users have a consistent view of any identity and that any impersonation attacks can be detected either at the time of the request or after the fact in an audit. And so if you go back to the example where the server was really trying to play Bob off against Alice by showing them conflicting versions of the tree, let's assume for a fact that Alice and Bob both got the same version of the root of the tree. Then they'd both work their way down to the same leaf of the tree using cryptographic hash functions, and finally would get to the same end of Alice's signature chain in both cases. So as long as Alice and Bob get the same root, they're going to get the same version for Alice's identity, and therefore the same signed sequence of statements that allow Bob to build up Alice's identity on his side. Now, there's one thing we need to be careful to support here, and that is Alice probably has a mutable identity. And that if she's known as Alice at company.co, she might eventually change her mind and decide she wants to change her name or she wants to switch potentially to a different organization within the company. So there needs to be another level of redirection. And the way we implement that is that we first store in the transparency tree a mapping of Alice's human readable identity, her email address, to her user ID, and then a mapping of her user ID to her last signature. And we're doing this again through some sort of hash function called H. Now, I've left out what this hash function is actually doing. We need to think a little bit harder about that. Well, it can't be a standard cryptographic hash function because that would leak too much data about how Alice's identity is changing to the other users in the tree. Instead, as first proposed in the paper Connix, we're going to use a verifiable random function, or a VRF. And in this case, a VRF functions in a lot of ways like a hash function, but has other important properties so that users stored in the tree can learn information about their neighbors. What is a VRF? Well, it's a one-way random function that only the server can compute, but all clients can verify. And you could think about one way to implement it is with a non-randomized signature. And there are a lot of evolving standards here, and you can see some IETF drafts for people actually working on practical solutions to building out VRFs. So that was our story for Tofu, or improved versions of Tofu, about how Alice is going to sync a notion of her identity to other people in her meetings, and that identity might encapsulate many devices, not just one. But how do we know who Alice is in the first place? Are we just taking Zoom's word for it? And so in this case, we want to build up to a new feature, which we're calling identity provider attestations. And so imagine Alice is in an organization that uses an IDP, or an identity provider. And we want to build up a system where Alice can have that provider sign off on what her identity is, rather than having Zoom be in charge of that. And this way, we've moved trust from the Zoom service into another service that Alice is trusting anyway. And this process looks a little bit like this. Alice could authenticate her IDP using something like the OAuth 2 protocol. And when she does that, she could post to it the tail of her sigchain, the last thing that she signed that was in her sigchain. When Alice goes to join a meeting, she can request the identity provider signature over her sigchain tail, which she then intends to show to other people in the meeting. When Bob comes along, he first checks that the identity provider is authorized to speak on behalf of Alice's company. So he's going to make a TLS connection to that company. In this case, company.com is associated with Alice's identity, and get some sort of URL that points to Alice's identity provider and also the public key of that identity provider. And finally, Bob can check the fact that the statement of Alice's identity has been signed properly, that it's reflecting an identity that he could show on a screen. And finally, this will encapsulate the identity that Alice was building up in the previous slides. So in other words, Bob can get Alice's chain tail as corroborated through a third party. So now he really knows this is Alice, not somebody who a compromised Zoom server is pretending to be Alice. So just to recap, to improve upon end-to-end encryption, we're building up a stronger notion of identity at Zoom. Users can have identities composed of multiple independent devices. Each of these devices has a private key that never leaves the device, but public keys that it's shared with all participants. Users can conveniently remember each other's keys and not on a per device basis, but more on a per user basis. Therefore, any warnings that are exposed in the UI are once per user rather than once per device. And finally, it's interesting to think about ways in which third parties can attest to these identities without having to trust Zoom. And we built up a mechanism through the OAuth 2 protocol where identity providers can do that rather than Zoom itself. And I wanted to provide a little bit of a teaser for the future. The applications for this technology goes way beyond meetings. We can think about the same technology basically at play in any context where Alice and Bob need end-to-end encryption. So you can think about async communications like messaging. So here's a recap of what we've learned today and what you can think about going forward. We think the most digestible nugget here is to think a little bit more about the risks surrounding point-to-point encryption or potentially on-prem solutions. And we'd like you to think about how you can share your knowledge of the core design concepts that we presented behind end-to-end encryption. Going a little bit further out, maybe think about your own product, your own organization, and how can end-to-end encryption benefit you? And maybe there's a class of threats that are quite important that you could use end-to-end technology to guard against. And if you have a little bit more time, you could check out our white paper. As I described, a lot of these details are covered in way more depth in that paper. And of course, if you have any comments about how we can improve the design going forward, we'd love to see them. And finally, within 6 months, you should be on the lookout for these new features landing in the app and more details to come on those. But we're really excited about the way that we can integrate a strong notion of identity with end-to-end encryption to provide better value for Zoom's customers. And that's all I had. Thank you so much. Thank you for your questions. We look forward to talking more about all the stuff we're working on here. Thank you.